Hi. So, what does 4.2 sigma mean? So you might have recently heard that the measured value of muon g minus 2 differs from the standard model expectation at 4.2 sigma. Or you might have heard that physicists typically don't declare a discovery until some observation passes the 5 sigma threshold. Or you might hear that physicists find some observation interesting because it differs from expectation by 3 sigma. So here we're going to talk about what these numbers mean. So the topic of this video is Gaussian errors. Now, this topic might not be as exciting as a new scientific discovery, but I hope to convince you that it's really important. Gaussian errors are a core concept in how a lot of scientific results, and not just physics results, are reported. So to understand new scientific results, you really need to know a thing or two about Gaussian errors. So there are lots of videos that are useful for understanding Gaussian errors on this channel. Here we're just going to give a quick overview, possibly a too quick overview. We will point to other videos with more detail at the end. So if there are things in this video that you don't understand, don't worry, there are other videos that go through the concepts more slowly and in more detail. Okay, so let's start talking about measurement errors. So we want to measure some observable quantity that we're going to call Q. So Q could be the mass of a particle, the lifetime of a particle, it could be muon g minus 2, etc. Now we're going to call the true value of Q, Q true. And we're going to call the measured value of Q, Q measured. Now, measurements are not perfect, and that means that our measured value, Q measured, is not going to equal the true value, Q true. And the error is the difference between these two quantities, Q measured minus Q true. Now, Q measured is what we're going to get from an experiment. But the true value, Q true, we don't know. And that also means that we don't know the error either. Now, while we don't know the error, we can make an estimate of how large we can reasonably expect the error to be. And this estimate is called the uncertainty. Okay, so as we said, here we're going to be talking about Gaussian errors. And we should point out early on that Gaussian errors are not applicable to every situation. But they do apply approximately in a large range of scenarios, and understanding Gaussian errors is also useful for understanding more complicated situations where Gaussian errors don't apply. Okay. So in talking about Gaussian errors, we're going to assume that there are many different potential sources of error. So some of these sources of error are going to push the measured value, Q measured, up relative to the true value, Q true. And other sources of error are going to push Q measured down relative to Q true. The total error is the sum of all of these different contributions. And in taking that sum, we have to keep track of the signs. So for example, if we have one source of error that pushes Q measured up relative to Q true, and we have another one that pushes it down by the same amount, those two would cancel in the total error. Okay. So in order to talk about these errors, we really need to talk a little bit about the random walk. Okay, so here's what a random walk is. We're going to take an object located at the position x equals 0, and it's going to take a series of steps. Each step is to the right or to the left by 1 unit, and it steps to the right or to the left with equal probability. The steps are independent of each other, and we want to know the location of this object after it takes n steps. Okay, so for n equals 0, the object is located at x equals 0. After 1 step, the object can be at either x equals -1 or x equals +1, and it will be at either of those two locations with equal probability. After 2 steps, the object can be at the positions x equals -2, x equals 0, or x equals +2, and after 3 steps, it can be at x equals ±3 or x equals ±1. Okay, so now let's look at where the object ends up after n steps. We'll start with the case n equals 1. So after 1 step, the object can be located at either x equals -1 or x equals +1 with equal probability. Okay, now on to n equals 2. So after 2 steps, there's a 50% probability that the object will be located at x equals 0. And there's a 25% probability that it will be located at x equals -2, and a 25% probability that it will be located at x equals +2. So let's see why it's more likely to be located at x equals 0 than x equals +2 or x equals -2. So there are 2 paths that can lead to the object being at x equals 0. The object can go to the left and then to the right, or to the right and then to the left. On the other hand, there's only one path that leads to the object ending up at x equals +2. In order to get to x equals +2, the object has to go right and then right again. And similarly, in order to get to x equals -2, it has to go left and then left again. And there's only one path that does that. So, as there are 2 paths that lead to x equals 0, and one path that leads to x equals +2, and one path that leads to x equals -2, the object is more likely to end up at x equals 0. Okay, so next let's look at the case n equals 5. So after 5 steps, the object can end up at x equals ±5, ±3, or ±1. Here we'll just look at a couple of examples. So there's only one path that can lead to the object ending up at x equals +5. The object has to move to the right 5 times. On the other hand, if you count them up, you'll find that there are actually 10 paths that lead to the object ending up at x equals +1. And so, after 5 steps, the object is much more likely to be at x equals 1 than it is to be at x equals 5. Okay, so here are the takeaway points. So the object is more likely to end up near the starting point than far away from the starting point. And to end up far away, the object needs to take many steps in the same direction, which is less likely to happen. Okay, so lastly, let's look at the case where n is equal to 100. For the case where n, the number of steps, is very large, a smooth shape starts to appear in the distribution. Here we've overlaid in red a Gaussian function, and you can see that it fits the distribution quite well. Okay, so what does this have to do with measurement errors? Okay, so let's say we're doing a measurement. And through careful analysis, we've figured out that there are 5 important sources of potential error. We've also figured out that typically they are of about the same size. And also, these sources of error are uncorrelated with each other. So, qualitatively speaking, some of these sources of error are going to push Q measured up, and some of these sources of error are going to push Q measured down relative to the true value Q true. We don't know which direction each of these sources is going to push Q measured. Now this is starting to sound a bit like a 5-step random walk. Now a 5-step random walk isn't actually that realistic. Different sources will not push Q measured up or down by the same discrete amount. So let's do this. Let's take the 5 sources of error to be of the same magnitude on average. We'll do a random walk where the step size varies. On average, the size of each step is 1 unit, as before, but it will vary randomly between 0 and 2. Okay, so then we'll do what are called toy experiments. So in our case, each toy experiment is going to be a computational simulation of a 5-step random walk with this randomly varying step size. And we're going to do 100,000 toy experiments and then plot the results. Okay, so here we've plotted the results of those toy experiments in the blue bins. Again, we have a random walk with a varying step size. The step size ranges between 0 and 2, but the average step size is 1. And what we're looking at is the position after 5 steps. Additionally, we've plotted a Gaussian distribution on top of the blue bins as a red curve. And we can see that the red curve fits the blue bins pretty well. So the Gaussian shape in the position is clearly visible. The object is more likely to end up near the starting point, and this is due to a partial cancellation between the different steps, or, as we're going to be interested in, the partial cancellation between different sources of error. Okay, so back to measurement errors. We have 5 sources of measurement error, and we estimated them to be all about the same size. And the different sources of error are uncorrelated. So, Q measured will be approximately Gaussian distributed around Q true. Now, I should note that this approximation fails if 1 or 2 sources of error are, on average, much larger than the others. So you have to watch out for that. Okay, so we've seen the Gaussian distribution crop up a couple of times, so let's take a look at that. So a function of this form is called a Gaussian, or normal distribution. It's a function of x, and it takes 2 parameters, mu and sigma. Mu gives the center of the distribution, and sigma gives the width of the distribution. Sigma also affects the normalization, so the height of the distribution. And it's taken a while, but we're finally seeing the letter sigma show up in this discussion. Okay, so here we plot 2 Gaussians. Both of them have mu equal to 0, so they're both centered at x equals 0. In blue, we give a Gaussian that has sigma of 1, and in red, we give a Gaussian that has sigma of 2. And you can see that the red curve is wider and shorter than the blue curve. Okay, so now we're ready to move on to Gaussian errors. Okay, so the measured value Q measured will be Gaussian distributed around the true value Q true. Let's see what this means. So let's imagine that we repeat the measurement many times. And we're going to take the errors to be uncorrelated between the different times that we do the measurement. In about 68% of measurements, Q measured will fall within 1 sigma of Q true. In about 95% of measurements, Q measured will fall within 2 sigma of Q true. And in about 99.7% of measurements, Q measured will fall within 3 sigma of Q true. Okay, so with that, let's move on to testing the standard model. Okay, so now we're going to consider the hypothesis that the standard model prediction for Q is in fact the true value of Q. So we're testing the hypothesis that Q true is equal to QSM, where QSM is the standard model prediction for Q. And we should note that for simplicity, we're neglecting the possibility of an uncertainty on QSM. But in general, the predicted value will also have an uncertainty. Now, if this hypothesis is correct, Q measured will be Gaussian distributed around QSM. So here we have the same plot that we had before, except that before the Gaussian was centered at Q true, and now we've replaced that with QSM. Okay, so you might be wondering, where do we get sigma? Well, this is estimated by careful analysis of the sources of error in the experiment. And I can't emphasize enough that this is not easy. With this carefully estimated value of sigma, we construct the Gaussian curve describing where we expect Q measured to end up. And this is the curve shown on the right. Okay, so far we've only talked about the probabilities that Q measured will fall more or less than a certain distance from Q true. And here we've taken Q true to be equal to QSM by assumption. These probabilities should be known before the actual measurement takes place. Okay, now it's time to do our actual measurement. So when we do the actual measurement, we will get a result that will differ from QSM by some amount. So on the right, we've shown the hypothetical scenario where the actual measured result lands at the location of the black arrow. And that actual measured result differs from QSM by the distance shown by the blue bar. Now, we can quantify the disagreement with the standard model expectation by taking the difference between the observed result and QSM in units of sigma. So here are a couple of examples. We could have a situation where the observed result agrees with the standard model expectation within 2 sigma. Or the observed result disagrees with the standard model expectation by 3.5 sigma. So if Q true is equal to QSM, and if the errors are Gaussian distributed with uncertainty sigma, 68% of measurements will fall within 1 sigma of QSM. And under the same conditions, 95% of measurements will fall within 2 sigma of QSM. These results are typically viewed as compatible with the standard model. And about 99.7% of measurements will fall within 3 sigma of QSM. This means that about 0.3% of measurements will fall outside this range. Results falling outside this range are sometimes considered evidence of disagreement with the standard model. And approximately 99.99994% of measurements will fall within 5 sigma of QSM. and that means that about 0.00006%, or about 1 in 1.7 million, will fall outside this range. For results falling outside this band, physicists may start talking seriously about discovery. And if the standard model prediction is correct, and the errors are Gaussian distributed, how often would the result fall more than 4.2 sigma away from QSM? So about 1 in 37,000 results will fall outside this range. If you did an experiment every day, you'd expect a result like this about once in your lifetime. So here we've covered the topic of Gaussian errors at a whirlwind pace. But there are a lot of resources on this channel that you might want to take a look at if you want to learn about Gaussian errors more slowly or in greater detail. So you might want to take a look at the hypothesis testing playlist, the random walk playlist, or the Gaussian statistics playlist. Additionally, the Minicourse on error bars, measurements, and decision analysis goes through a lot of what was in this video, but in more detail. And lastly, you might be interested in the video 5 sigma, the standard for discovery in particle physics.